with our thermal method, being able to move data remotely is a really powerful tool. And being able to evaluate data that can be halfway across the world in real time is incredibly powerful as well.
Good day. Welcome to the Steel and Dirt podcast. Today we have Ryan Allin of Pile Dynamics, and we're going to learn a little bit more as they prepare to celebrate a 50th anniversary in the industry. Good morning.
Good morning. Thanks for having me.
We spoke the other day a little bit, trying to understand where PDI Pile Dynamics is, and there's a GRL was a company that you're affiliated with that I've worked with in the past. And I was not clear that they're two separate entities, and one is operations and field work in the pile driving industry, and Pile Dynamics, they're more scientists and inventors and manufacturers. Maybe explain that a little.
It's interesting because if you talk to our principals, Frank and Garland, the big question when they kind of developed the high strain testing method was, do we do the testing or do we sell the equipment? And the ultimate answer was they needed to keep the lights on in the office. So if someone called to buy a system, they would sell them a system. And if someone called that needed testing, they would go out and do the testing. So it became apparent that they needed two companies, one to actually manufacture the equipment, the other one to actually perform the testing. And it's been a good dynamic. It serves purposes in that it allows the testing firm to kind of maintain a standard of quality. So with GRL, we can basically set a standard of what dynamic testing or any of our other test methods should be. And at the same time, then we have the ability to then sell the equipment globally to basically GRL's competitors.
Right, which have now become part of the same family through Pile Dynamics, right? I mean, they're facilitating the same implementation in the field, and it's just to allow Pile Dynamics to have a global reach. I think that's a really beautiful story. My whole interest in this podcast was really educational, and for the next generation to understand, where we started and where we're going. Early on, pile driving examples were mostly in warfare, where even back to the times of Caesar, when he was a young warrior, a driving pile to build bridges across rivers to sack a new city, right? And
Yep, the Gallic Wars.
how did he test his pile? Well, elephants, just his men, right? So there really wasn't a way to understand what type of capacity you had until you did what we refer to as the full scale test.
Yeah.
So now maybe help us with some insights onto why what you're doing is better.
Well, yeah. I mean, you go back historically, we basically beat on something till it wouldn't go no more, right? Nowadays, we want to be more efficient in our use of foundations. We want to make sure that we can deliver a cost-effective foundation. So when we talk in terms of where dynamic testing fits in, it really is trying to bridge a gap to try and bring a reliable solution to estimate the capacity of the pile in real time, but do it at an economic cost. You basically have the pile driver already there beating the piles into the ground. And so through our stress wave measurements, we can actually collect that data and actually analyze it in real time to calculate the capacity of the pile. So that research started in the 1960s, which seems like a long way away. But really, it was the first time that we had the technology available to collect that data. And so over time, they basically built a database of showing the reliability of it. And it's kind of become an accepted method, especially with highway work, but also private industry, where it's used kind of globally as a reliable means of estimating capacity.
Well, and it started in the 60s and 70s, and with your team, but wasn't there some in the 40s? This Carl Tazagi. Can you tell me some more about his early studies that kind of broke this wide open or made this possible?
Well, Terzaki would have been kind of the person that developed kind of the groundwork for geotechnical engineering. But really, if you want to talk in terms of what we're doing with dynamic testing, it really kind of goes back to the work that EAL Smith did, and he was actually a mechanical engineer with the Raymond Foundation Company. So Raymond was at one point the largest foundation company in the world, and uh, be, being a mechanical engineer, you know, he basically looks at the world as a bunch of springs and elastic rods. So he essentially started looking at the pile as basically a spring that's going to deform under load. He started looking at the soil as basically a spring that's going to deform under load, and he created this model of basically creating a fairly reasonable model of how the pile is going to behave during a dynamic impact. And so it was really his research that laid down the foundation of what became the dynamic testing. He was really ahead of his time when he basically published his wave equation in 1954. Unless you had like an army of graduate students that were willing to, you know, sit there and process second order differential equations, he was it was really an exhaustive process. It took about 25 years for technology to catch up with him before we actually had PCs that could run it on a personal basis. An interesting fact is that when he published that initially, IBM actually brought him up to Binghamton, New York, and actually coded that into a program for the first time back in the 1950s. And there's fairly good evidence that that may actually be the first computer program that was written for a non-military application.
No, that's fascinating about Mr. Smith. I had not known that, but it makes sense because I remember when the first time I saw Pat attach transducers and accelerometers to the pile in the early '90s. It was I tell you, it was probably one of the first times I ever saw a laptop on top of a barge deck. Right, it just
Yeah,
didn't
yeah,
exist much,
yeah,
and how the wave energy wave dissipates to the end of the pile, and it just incrementally moves forward. And before that, I always thought about driving a nail or driving a pile, that it's the tip that's kind of pulling forward, but it's the top that pushes the tip that brings it down. And to understand how that works in a wave and a spring, as you explained, that Mr. Smith theorized, that it starts to make sense. But is that, do you still use accelerometers and transducers, or something more
yeah.
sophisticated now?
Yeah, it's I mean, obviously everything evolves, and so the accelerometers and the strain gauges that we were using around 1990, you know, we've eclipsed those in terms of their capabilities, and we've made them smaller and more reliable than what we had back then. But yeah, we're still hooking up the accelerometers and the strain gauge to the top of the pile to measure that stress wave.
Now, you've moved from the pile driving industry towards drilled shafts. Tell me about the shape program.
Yeah, so I mean, the big schema thing is to try and add quality assurance to those drilled shafts, so we actually understand better what we actually have down there, and that the finished product is as close to the design as intent as at least possible. So our methods for testing this then would be to try and test the shaft before we cast the concrete and potentially afterwards. So we have our shape system, which is our shaft area profile evaluator, which basically uses an ultrasonic pulse. In fact, it uses 8 ultrasonic probes to basically send an ultrasonic pulse to the sidewall and then bounce back. And then at the same time, it's measuring the wave speed of the slurry continuously. And so, knowing the wave speed and having that time interval between the ultrasonic wave being sent and bouncing back, we can actually get a sidewall measurement, and we can do that fairly rapidly. So, you basically have 8 probes that are basically radial around there that are sending a pulse out and then taking a measurement about once every second. So, that fact, if you want a resolution of about 1 foot, If you think about a 60-foot long shaft, you could have that shaft tested both down and back up in 2 minutes. So it's a very quick way of evaluating that the shaft has maintained its verticality and that you have an adequate diameter versus depth.
So now you've done your shape. You've got a really quick way of analyzing the size and contours and acceptable irregularities in a drilled large diameter drilled hole into planet Earth. And we're doing that now with your shape initiative. So now we can put our rebar cage in there, and it's go time. We're pouring tremie. Now we're putting conduits in there so that we can do cross sonic logs or measuring of after the fact and hydration and that was problematic too, because early on we were using PVC because it was cheap, and then that was like delaminating just a little from as the concrete would shrink, and or who knows if there was even some kind of reaction there or whatnot. But so that was throwing the data off. So there was a lot of drilled shafts that were cored, and it was something that was up in the data in the cross sonic logs. So help me understand where we're at with that technology, because that was another reason why I just always have been. I'm a pile driver. I really don't care to do those, and I think you've kind of simplified that.
Yeah, so we still make our crosshole equipment, and it's still a popular test. But starting around 2000, actually in the University of Southern Florida, Tampa, they started doing research under the Professor Gray Mullins there, looking at temperature and its correlation to integrity. And eventually, we ended up partnering with them around 2010 and came up with what we call our thermal integrity profiling system. And this is a proprietary system that Dr. Gray Mullins has patented. But basically, it looks at temperature measurements versus depth. And so, what we can do is we can take a wire that has a node on it every foot and install that into a rebar cage. And that basically is just zip tied on. And so, you would put that in the cage in lieu of a CSL tube. And taking that temperature measurement, we can then collect that data and push that up to the cloud and effectively look at a temperature measurement versus depth. And so you could have one wire in the shaft, you could have 20 wires in the shaft, but basically the larger the diameter shaft, the more wires you would put in it. And the idea being is if we have consistent temperatures versus depth, we would have consistent quality concrete. If we have some sort of inclusion or poor quality concrete, you would see that as a reduction in temperature. And so it's been a very popular method that really in the last 2 years has caught on, largely because it overcomes some of those limitations with CSL. We don't see that debonding issue that is so prevalent. And in fact, if you go back, some of the initial research was funded because they were looking for alternatives to doing CSL testing. So it's really a method that's become quite popular, largely because we have the ability to move data up to the cloud. We can monitor the foundation remotely, and we can get results back, within 24 to 48 hours, knowing whether that shaft is a good shaft or not.
Where does Squid lie in all this?
So Squid would kind of be it would be a complementary test to the shape. The shape is evaluating the sidewall, but we want to make sure that we have adequate clean out at the base of the shaft as well before we cast the concrete. And the means of doing that have always been somewhat interpretive. There's some areas where they'll just drop a weighted tape measure down to the bottom and try and get a feel for it. And if they feel there's debris down there, then they'll try and correct that. There's some states that use an SPT rod with a sampling spoon to try and get a feel of what that is. And of course, there's a diving bell system where they actually put a camera down at the bottom and try and get an image at the bottom of the shaft. Our feeling, again, was to try and improve the method by making that test quicker and giving you quantitative results. And so shaft quantitative inspection device is what it stands for. Um, so when you utilize this, you basically have a penetrometer and a displacement plate, and basically the plate will stay on top of any debris. And as the penetrometer goes forward, we'll actually measure that displacement, and you'll end up with a force versus displacement plot to allow you to evaluate what that debris layer thickness is. And so it basically has three penetrometers on the bottom of it, and you basically would run it down, and you would use the crowd force of the crane to push down on that, and you would get a fairly quick measurement on what that debris layer thickness is. The nice thing is it attaches directly to the Kelly bar with the drill rig. So if for any reason it's inadequate clean out, it's just a matter of running it up to the top, swapping out, put the clean out bucket on, go down there, try and get that debris out of there, and test it again. And again, as we've moved forward, it's getting rarer and rarer that we would actually send someone down to the bottom of the shaft to inspect it, with safety regulations what they are these days. So to be able to see that remotely and get a better quantitative measurement is really, I think, important these days.
Oh, for sure. So we've got on the drilled shaft. So we've got shape to understand the quality of the hole before we go in, and we've got squid to understand the quality of the bottom, which is most drilled
Yeah.
shafts. That's where most your capacity is versus driven pile, right?
Yeah.
With understanding the wave equation, and is there something new afoot there? I see a lot of the pile these days are different shapes and hollow concrete pile. And when I was coming up through the ranks, we drove a lot of steel pile. Yeah, we drove concrete pile, but it was usually square. I've driven cylinder pile, but now, which is huge, right? Now there's these mid-size, 36 and 30-inch concrete, octagon shaped hollow, and there's lots of different variants. Does any of that, does that change what you do with the pile driving testing in any
Yeah,
way?
there's a lot of considerations that have to be taken for that, and that's really kind of where the research needs to go. As you stated, the idea of driving a 36, 48-inch pipe pile, 20 years ago, that was very uncommon on shore. That was basically an offshore pile. Now you're seeing that's not really out of play anymore, and so looking at the behavior of those and how they drive. Versus how they perform statically, you may have two different conditions there. And so getting a better understanding that of how those are going to behave during a dynamic impact versus a static load test, that's really important. There's a lot of research that needs to be made there. And so that really is kind of the area in terms of the driven pile industry of where research needs to be done. The other thing to think of is the use of vibratory hammers, and that's becoming more and more popular to install foundations, and how does that affect the static capacity, and how can we actually take measurements from vibratory installation and correlate that to some static capacity. Again, that's a big topic of research right now.
It all depends on the soil, right? I mean, when it's vibrating, it's my understanding that the mechanism is thixotropy, where thixis is Greek uh, for shaking, and atropy is change, right? And so it is instantaneously, really liquefies the soil at the very tip, and the hammer basically is just a gravity weight along with the sheet self weight to just pull it towards the center of the earth, right? So
Yeah, that's right.
it's just an instantaneous liquefaction, which which works great in sand and silt. But it's something that's always been interesting to me is in clayey soils that they have an actual electric affinity. The soil particles have an electrical affinity to water. So they don't shake it. You can't shake the water out of
Yeah,
clay. I've seen a lot of equipment torn up because people just wait too long. They're just like, no, we're just gonna put bigger bias plates on there and wait a little longer. And it's like, guys, let me tell you, in the world of physics, it isn't going to happen because of the way that it functions, right? So uh, uh, you gotta drive it through. You gotta beat it through, right? And I'm a big fan of vibratory driving, and but there is a problem with what do you have when you stop? How long does it take that energy to dissipate?
And what how are there permanent changes to the soil after it's been vibrated in, and how long does it take to regain that capacity? So a lot of times, that they would take it down part of the way because you can get them in faster that way, and then you get back on it with an impact hammer and drive them home, as they say, with the impact hammer. So, but you're right. I mean, there's no uh, perfect universal solution for all foundations, right? There are certain foundations that are going to perform better in certain soils, and there's other foundation types that are going to perform better in other soils, and the same thing's true with the means of actually installing those foundations.
Right. So the current test for a vibrated pile is to put a hammer on
Yeah, yeah,
it, isn't it?
yeah,
Because I mean, so
yeah,
many times I've
basically.
been on so many jobs, so many years, and it was always a negotiation with the owner's engineer. How many times do I got to beat this pile after I vibrate in place? Because maybe we're just installing trestle and it's a means and methods. We have to
Yeah,
get a big crane in this spot where we're building a bridge, and we're building the bridge because we can't build a road and there's not enough water to float anything. So we got to build a temporary structure to get to the structure that you want us to build. And the good news was a lot of that was never dictated to us as builders, and a lot of times, depending on the soil, we would just vibrate it in, and but we would do our own testing where we would, in the first couple of bents, we'd vibrate and then we'd impact to see what we got, right?
yeah, yeah.
And then we'd
That's right.
vibrate to a different elevation, impact, see what we got, and then we get a feel for it, and then we just go, and then we're just relying on the vibrator. However, there's some soils, particularly like the Cooper Marl up in South Carolina, whatnot,
Yeah,
has those
yeah,
pore pressure problems that you can lose capacity. You don't always have exactly what you think you have. There's just some soils that are different, right? So I think it's great that there's research going on there, because that's it's still a puzzle,
yeah,
and it's a
yeah.
function of the geology. And I certainly don't know what the solution is, but the smart people like you, Ryan Allin, and your colleagues at Pile Dynamics. I'm glad to hear you're working on this.
Yeah, yeah. I mean, I guess that's the fun of geotechnical engineering, right? It's always an adventure. Every time you go out there, every soil's different, and just when you think you have it figured out, you're proven wrong. So it's kind of the joy of geotechnical engineering is it's not all figured out. You talk about a structural engineer, you can predict how a beam is going to deflect to the thousandth of an inch. We're still dealing with to the nearest inch a lot of times when we're talking about soil. So I think it's a great area of field of research. I wish it was more heavily promoted in our universities, because a lot of times you see people gravitating towards other fields of study. But I think geotechnical engineering has a lot to offer.
I've always found that fascinating. For any young people out there listening, civil engineering, geotechnical engineering, these types of fields, and mechanical engineering, paying some homage to Mr. Smith. These fields open up questions, right? And we have questions about behavior and how we can build most efficiently, and understand once we build it, we just want it to last. Well, how do you know that? Well, you put guys to work like Pile Dynamics, who are doing the research, who are producing new products, who are asking the right questions, and working with universities. So I think that's a beautiful story. I guess that's what you're approaching 50 years of an anniversary. I wonder what the next 50 years are gonna bring.
Yeah, that's a great question. Yeah, I think one thing that comes to mind is with our thermal method, being able to move data remotely is a really powerful tool, and being able to evaluate data that could be halfway across the world in real time is incredibly powerful as well. not just from the aspect of the testing engineer, but really it makes a lot of sense for the whole project. You think a contractor, if they have assurance that they have a good foundation early on, they can move on to installing the next foundation. If there's a problem, they can adjust their construction methods to prevent that problem from happening again early on before they have to go into remediation for a whole bunch of foundations. So, you know, as is everything in the world, the ability to move information faster is a critical thing, and every revolution that we've had in the history of the world has been basically precipitated by the ability to move that information faster. So I think the idea of moving things into the cloud and being able to evaluate things in real time remotely is going to be a big key in how we look at things in the future.
Well, I'm just wondering if with that type of thermal information on the cure on your shafts, do you have a good correlation to cylinder breaks then to the thermal information?
Well, I mean, the one thing it does give you is the ability to get data from the actual in situ concrete that you have there, right? So, we would basically be able to see that hydration process as a function of time and temperature. Uh, when we basically see that data start to normalize, that temperature effectively start to cure down, we know that hydration process is basically done. So the concrete's effectively coming up to strength at that point. And of course, those bonds continue over time, but you'll definitely see a time peak, and then those temperatures start to cool off. So you basically have reached the finality of that. So having that information basically gives you some correlation in terms of that strength. So, do we have any direct predictions of elastic modulus? No, we don't have that, but certainly that's something worth pursuing and looking at.
And I'm just wondering that if there's not some applications for your technologies in pouring some of these big mass pours, at least trying to understand the bottom in a better way. I don't think the contractors would like it very much, but I think the engineers would like to have some peace of mind, because there's been some catastrophic problems with Tremy pours over the years, especially like large ones, bridge bascule spans. I could say one. I know there was a big one up at the Woodrow Wilson. The whole thing, the guys got done pouring 1,000 yards, and all of a sudden, as they're departing after a good 18-hour shift, the whole, you know what I mean, the
Oh
whole
no.
thing moved, right. So these things happen, and they could be more preventable, potentially.
Yeah, I mean that. Interestingly, the reason why it was initially thought of was to push the penetrometer actually into the soil underneath and get a better idea of the strength of the soil under the shaft. And we have done that in a limited scope. The Gordie Howe Bridge that they're building up now between Detroit and Windsor, they actually required them to push those penetrometers into the shale bedrock there to ensure that they were on the competent shale instead of in the weathered zones. So they've utilized it in that regard to kind of verify the strength of the soil under the foundation. But you're right, there's a lot of applications there that could go into mass pores and kind of trying to see what's happening down there at the bottom before the problems are trying identify the problem before the problem creates a big problem.
Well, listen, I congratulate you on approaching your 50th anniversary here at Pile Dynamics. I know it's not your 50th anniversary there, Mr. Ryan Allin, but you've been there a while, so you're a senior member of the team, and we appreciate you spending some time with us here on Steel and Dirt podcast. Hope we could do this again.
I appreciate the opportunity. Thanks for having me.